Picture this. It's the year 2500. The first probe to leave the Milky Way is finally passing our galaxy's outermost star. A historic moment that's being broadcast to every settled planet. The probe's name is Wanderlust 1. Its destination, our closest neighboring galaxy, Andromeda. But just as onlookers celebrate, something strange happens. Impact. Worlds watch in shock as the middle of the probe crumples in on itself, causing its metal to distort, buckle, tear, some vanishing entirely. The remains of the probe start spinning in space, its systems dead. And then the culprit becomes clear. Wanderlust 1 was hit by a primordial black hole. Of course, what I just told you is fiction. But tiny black holes with masses so small they are comparable to an adult rhino might not be. They could be out there, circling our galaxy's edges, and we may have just found proof that they actually exist. I'm Alex McColgan, and you're watching Astrum. Join with me as we delve into the darkness to solve the mysteries of primordial black holes. What are they? Where do they come from? And should we be worried? For a long time, tiny black holes, what I'm going to call black hole rhinos, seeing as they could have around the same mass, were thought to be impossible. Until the 1960s, we knew of exactly one way to make a black hole, and that was through stellar collapse. A star 20 times the mass of our sun or greater, running out of fuel and exploding in a supernova. All that exploded matter collapses, leaving behind an object so dense not even light could escape from its crushing gravity. This is a black hole. And because it formed from a star, it's a stellar black hole. But this isn't how all stars end. If their mass is less than 20 times that of the sun, it still goes supernova, but the collapse isn't quite powerful enough to create a black hole. Instead, we see a neutron star, a tiny celestial object that's still incredibly dense and made up almost entirely of neutrons. And for stars smaller than 8 stellar masses, they don't go supernova at all. So there is a limit to how big stellar black holes can be at birth. No larger than the largest stars, maybe a few hundred times the mass of our sun, and no smaller than a few times more massive. So why do we think that smaller than possible black holes could actually exist? Strangely, the answer is that we discovered bigger than possible ones. Today we know that at the heart of almost every large galaxy lies a gargantuan monster, a supermassive black hole. Back in the 60s, we were just beginning to discover these enormous beasts. The first quasar, a highly luminous and red-shifted galactic center, was found in 1963, kickstarting a roughly decade-long golden age of black hole research. The first predictions of a massive black hole at the center of a galaxy came in 1971. As the years passed and more evidence of these titans came to light, we realized they were mind-bogglingly massive, hundreds of thousands to billions of times the mass of our sun. But they are something of an enigma, and left scientists with one question in particular: how do they form? While it's technically possible that a stellar black hole could consume mass and eventually grow this big, this explanation started to break down as examples of supermassive black holes from earlier and earlier in the universe's history started showing up in our increasingly distant images of the cosmos. But for now at least, there wasn't a better explanation. Then came the James Webb Space Telescope. Launched on the 25th of December 2021 and switched on in 2022, it promised to see further and in better detail than any telescope had ever seen before. It would look for stars so distant their light had started traveling at almost the dawn of the universe. And James Webb did not disappoint. These little red dots represent galaxies with supermassive black holes from just 500 million years after the Big Bang. Scientists realized this was not enough time for stellar black holes to grow to that size, not without devouring matter faster than the laws of physics should allow. Now, I've made a video on this idea before, and there is some evidence that this can happen, that black holes can disregard our speed limits on how fast they can eat to grow at rates we wouldn't initially have thought possible, that is, if we hadn't seen them doing it. But there are plenty of scientists who are skeptical of this answer, and there's an alternative theory, one that another recent James Webb discovery may have just confirmed as true. When it comes to forming a black hole, the key is density. When density is high enough, mass becomes so compact that its localized field of gravity passes a tipping point, and the speed at which you would have to move to get away from it becomes impossibly fast, i.e., you'd have to travel faster than the speed of light. The question is, how does matter get that dense in the first place? For that, you need a huge amount of energy, enough to overcome the electromagnetic force that stops electrons or protons from getting too close to each other. Then there's the neutron degeneracy pressure, a quantum mechanical force that says that two subatomic particles, two neutrons, can't occupy the same space at once. Neutron stars are not dense enough for their gravity to overcome this pressure, but they are still so dense that a spoonful of this matter would weigh as much as Mount Everest, over 900 billion kilograms. To make a black hole, you need forces able to crush the whole of Mount Everest into that teaspoon and then some. In fact, Mount Everest would have to be squashed into a space more than 1,000 times smaller than an atom to become a black hole. In the universe, as it exists today, such forces only exist in very specific circumstances, inside collapsing stars as they turn supernova. But go back in time, and that wasn't always so. Let's rewind to the earliest moments of the universe, within the first second after the Big Bang. There, those pressures did exist, albeit just for a moment. In this hot, dense particle soup, the distribution of matter was not completely homogeneous or evenly distributed. There were areas of high particle density and others where it was lower. Scientists believe it's possible that in particularly dense patches of space, black holes could have formed from primordial matter itself, skipping the star phase entirely. The result is called primordial black holes, and surprisingly, they aren't actually a new idea. They were first predicted in 1966 by Yakov Zeldovich and Igor Novikov. What's interesting about them is that they could have formed with masses 100,000 times greater than that of our Sun. This would be more than enough to account for the supermassive black holes that we see today, especially given the billions of years they've had to grow. Curiously, they didn't have to form as giants. They could also have been much smaller. A black hole the size of a single atom, with mass comparable to an asteroid, or a so-called black hole rhino that would be no bigger than a proton, but the mass of a rhinoceros. However, this was 13.8 billion years ago, and there are two problems with the theory that such tiny black holes exist today. The first is Hawking radiation, an extremely long wavelength of radiation that Stephen Hawking hypothesized black holes emit, gradually shrinking them over vast timeframes. It essentially tells us that, by now, all tiny black holes should have evaporated away. The second problem is that we haven't proven that primordial black holes actually existed in the first place. We've never seen a black hole arise out of the interstellar dust, or at least we hadn't until recently. In July 2025, NASA reported that the James Webb Space Telescope had seen 2 early disk galaxies, likely in the process of crashing into each other. But strangely, between them, and not in the center of a galaxy of its own, was a supermassive black hole. It had not somehow been ejected from either galaxy. They also have their own supermassive black holes, which left this third one completely inexplicable. The team who found it proposed that the black hole formed in situ via the direct collapse of a gas cloud. But this isn't the only evidence that black holes can simply appear given the right conditions. QS01 is a supermassive black hole that was also spotted by Webb. It inhabits a surprisingly small galaxy. Scientists were able to do spectral analysis and found that it's incredibly low in heavy metals, elements other than hydrogen and helium. This galaxy had less than 1% of the oxygen that we see in our own, and researchers called it one of the most chemically unevolved systems found in the early universe, which is telling. Stars usually produce these elements in just their first few generations, so the fact that they are absent in QS01's galaxy suggests that very little stellar formation has taken place yet, compelling evidence that wherever QS01 had come from, it had likely not been birthed by a star. Now, although not smoking guns, these 2 examples lend weight to the idea that the early universe was capable of producing primordial black holes. In fact, this finding may explain where all supermassive black holes came from. And if that's true, then it's almost certain that super tiny black holes used to exist too. But they're all gone, right? By now they should have dissolved. Well, according to one theory, perhaps not. Astronomy has a problem on its hands. As we track the amount of gravitational pull in the universe, it is much higher than it should be. Scientists conclude that there is additional matter inside galaxies, or circling them in large halos, something they've dubbed dark matter, because we can't see it. But you know what else carries serious mass and is quite hard to see? Black holes. Particularly ones with no accretion disks, because they formed directly out of interstellar matter. Of course, scientists have investigated this idea, and there's no evidence of large black holes surrounding the Milky Way, thankfully. If there were, stars would go flying like bowling pins every time one fell into our galaxy. We'd also see the light from stars behind them behaving strangely through the power of gravitational lensing, as the intense gravity of these black holes distorts the space around them. And we simply don't see anything that matches up to this. But tiny black holes, our black hole rhinos, would be very hard to detect through either means. There's no proof they're not there. The only argument is to say that they would have all dissolved by now. But this might not be the case. In April 2024, a study published in the monthly notices of the Royal Astronomical Society found that at tiny levels, Hawking radiation might slow down considerably, almost stopping entirely, which means these black holes might shrink and shrink until they eventually stop. Which, if true, means that black hole rhinos might be out there. Many believe dark matter circles our galaxy in a massive halo. What if, instead of all of that, it was tiny black hole rhinos? There could be millions and millions of them out there. A black hole minefield lying invisible and deadly. A swarm we could someday encounter if we ever attempted to leave the galaxy to explore another. We might be caged here without knowing it. Of course, space exploration has plenty of dangers all of its own, but it's more than unsettling to consider that as we voyage out into the dark, we could be on a collision course with a tiny, microscopic black hole with the mass of a rhino, or that one could be hurtling through space, on its way towards us. Let's hope we find some evidence that this particular theory isn't true, or at least forget the idea of leaving the galaxy. I think I'd rather stay at home. Have a look at this beautiful image captured by the James Webb Space Telescope. Immediately you'll notice two types of objects. First, you'll see the nearby stars within our own Milky Way galaxy, which look like points of light surrounded by diffraction spikes. But further in the background, you'll see entirely new galaxies, each containing billions of stars smeared out into elliptical or spiraling blurs. What you probably won't see are distinct, individual objects within those other galaxies, as they are far too distant and blend in with all the other sources of light. But there is one exception to that rule. One type of object that is so bright you can make it out from billions of light years away. So bright that it stands out from all the surrounding stars in its galaxy. A quasar. But what if I told you that a whole bunch of tiny quasars were hiding in plain sight, right within our own Milky Way? How can that be when they are some of the brightest objects in the universe? In this video, we'll get to see how that's possible, and how a team of scientists used images of just one nearby microquasar to gain a deeper perspective into the inner workings of quasars all over the universe. I'm Alex McColgan, and you're watching Astrum. Join me today as we unravel the story of these astronomical lighthouses, one cosmic photon at a time. Astronomers have been pointing their telescopes up at the night sky for centuries. Yet, it was only in the 1950s that they set out on a quest to map out what the universe around us looks like in radio waves, rather than visible light. Think of this as the astronomers' version of putting on night vision goggles. At first, they didn't see anything out of the ordinary. Many of the same galaxies that emitted visible light also emitted radio waves, so they could be seen with or without the goggles. But then, among the stars and galaxies that were known to populate the night sky, astronomers saw something new, something that shone very brightly in radio waves, but had never before been seen in visible light. And there wasn't just one of these objects. By 1960, observations quickly grew until hundreds of mysterious radio sources had been recorded across our sky. At the time, astronomers didn't have a clue what the origin of these radio waves could be. For all they knew, the waves could come from a giant intergalactic network of alien radios. But what they did learn from follow-up observations using more precise telescopes like the Hale telescope is that you could see these objects in the visible part of the spectrum. They were just extremely small and faint. They were far too small to be galaxies. They appeared as points, not smeared out blobs in the sky. But they also couldn't be regular stars, because regular stars don't typically emit much energy at all in radio waves. For this reason, these mysterious objects came to be known as quasi-stellar radio sources, which quite literally translates to something like a star, but not a star, that emits a lot of radio waves. That name eventually got shortened to something that was a little bit more palatable: quasars. Even with the catchy name, it took astronomers and physicists nearly 30 years to really pin down what these quasars were. And unfortunately, it's probably not alien radios, although the real answer is still extremely fascinating. It turns out that the explanation centers around black holes, and not just ordinary black holes, but supermassive black holes that can be millions or even billions of times the mass of the Sun. Such supermassive black holes are frequently found at the center of large galaxies, and although black holes can't emit any light themselves, they can make quite the spectacle out of the accretion disks orbiting around them. If you want all the details, you can queue up our older video on quasars here, but for now let me just give you a quick summary. Matter orbiting a black hole can spiral inward as it loses energy due to internal friction. Much of that energy ultimately gets converted into light that streams outward from the black hole. But in some cases, The accretion disk also splits out relativistic jets of ionized matter, collimated by powerful magnetic fields along with the spin of the black hole and its surroundings. The particles in these jets can propagate through the universe from galaxy to galaxy as cosmic rays, sending out radio signals as they're pushed around by intergalactic magnetic fields. Overall, quasars emit so much energy that a single quasar in a distant galaxy will outshine the other hundreds of billions of stars in that galaxy combined. That's why, when quasars were first observed, they appeared as small as a star, but far brighter than any star outside of the Milky Way could have ever been. Now, the Milky Way has its own supermassive black hole right in its center too, called Sagittarius A star. But for better or for worse, the accretion disk around our black hole is too thin and faint to call it anything close to a quasar, and until something dramatic happens, like the collision with the Andromeda galaxy that's scheduled for a few billion years in the future, Sagittarius A star will likely remain calm and mellow. On one hand, we're kind of lucky, because a quasar that close to Earth would emit enough high-energy radiation to be potentially fatal to terrestrial life, which makes you wonder about the kinds of life that could arise in galaxies that do contain quasars. But on the other hand, we're missing out on a second source of light in the sky, illuminating our planet almost as brightly as the sun, and it would be so cool to get to study a quasar from up close. So can you imagine my surprise when I learned that we might actually have the best of both worlds? Quasars, alive and active in the Milky Way, and yet not so powerful as to wipe out our entire biosphere. How could this be possible? If the one supermassive black hole at the center of our galaxy isn't a quasar, then where could they be? It took a couple of decades, but scientists eventually discovered that quasars can form around ordinary black holes too, not just supermassive ones. These ordinary black holes, just a few times more massive than the Sun, typically form when giant stars collapse, so there are loads of them spread throughout practically any galaxy. You probably wouldn't expect one of these black holes to have its own accretion disk, but once in a while, a nearby orbiting star might get sucked into its gravitational pull and act as a source for the smaller, less deadly version of a quasar, a microquasar. Even though the jets of a microquasar are much weaker, they can be easier to study because of their proximity to Earth, allowing us to learn more details about the properties and dynamics of both microquasars and their larger, full-scale counterparts. The very first microquasar was discovered in 1979 and was given the obvious name SS433, as it was originally documented as the 433rd entry in a catalogue of stars compiled by astronomers Nicholas Sanderlich and Bruce Stevenson 2 years prior. To date, only a handful of microquasars have ever been found, and SS433 in particular has been a subject of widespread wonder and research. Despite its name, SS433 is more than just some ordinary star in a catalogue. It is a Type A supergiant orbiting around a stellar mass black hole in a binary system. As the black hole accretes material from the supergiant star, it produces a pair of jets perpendicular to the line of sight from Earth, meaning that the jets themselves will never actually hit us or reach our detectors. But as the jets propagate outward, they emit light in all sorts of directions, allowing us to image them at various wavelengths and learn more about how they are produced. One of the first things we saw was that there are actually two types of jets emanating from SS433. The inner jets extend out just a couple of light years from the black hole before fading away, while the outer jets appear 75 light years out and span an additional 300 light years or so. We still don't know how exactly these outer jets form, or why they terminate after 300 light years, and we only have a rough idea of what they're even made of. But a recent study from the Hess collaboration gave us some new clues to answer these questions. One such clue is the presence and distribution of high-energy photons called gamma rays being emitted by SS433. Ordinarily, stars or accretion disks would not be expected to produce any gamma rays because their temperatures are far too low. But the outer jets coming out of SS433 seem to emit them in spades. What's even more surprising is that even though the outer jets are extremely hot, the spectrum of light that they're emitting isn't consistent with an ordinary thermal distribution of photons. So, what's generating all of those gamma rays? The current theory is that the outer jets contain high energy electrons that can bump into lower energy photons passing through the system, and they transfer their energies to the photons during those collisions. This process goes by the name of inverse Compton scattering. The scientists at Hess realized that measuring the energy in these emitted gamma rays can give us a lot of information about the energy of the electrons in the jets that produce them in the first place. And what they found was in full support of the inverse Compton scattering theory. The highest energy gamma rays, carrying over 10 tera electron volts of energy per photon, or about 10 trillion times more energy than a photon of visible light, were primarily coming from the innermost region of the outer jets. Gamma rays with lower energies, on the other hand, came from correspondingly farther distances down the jets of S433. This distribution is a clear indication that electrons farther down the jets have less energy to transfer to photons than electrons right at the beginning. Or in other words, as the electrons stream along the outer jets, they tend to lose energy over time, presumably due to their collisions with photons. But how did the electrons acquire such large energies to begin with? Models suggest that their initial launch velocity from the black hole was just about 1/4 of the speed of light. But by the time they reached the outer jets, these high energy electrons appear to be moving at speeds greater than 99% the speed of light, multiplying their initial energies by a factor of 1 billion. The Hess collaboration believes that this wild acceleration occurs due to a shock wave at the base of the outer jets caused by complicated configurations of magnetic fields. Each time an electron interacts with the shock front, it gains a boost of speed as if it crossed a boost pad in Mario Kart. And due to the diffusion of electrons back and forth within the jet, some electrons can cross over this boost pad over and over and over again, like an infinite speed glitch. This process is called diffusive shock acceleration, and it may be responsible for amping up electrons to energies in the hundreds of tera electron volts, just enough to be able to produce the high energy gamma rays observed by Hess. But shedding light on the production of photons within the outer jets of SS433 is just the beginning. Microquasars scattered throughout the Milky Way can hold treasure troves of information about the inner workings of even the most massive quasars in the center of distant galaxies. And now that we know to look for them, microquasars are less like hidden gems and more like beacons in the sky, posing for our astronomers to capture their beauty in an entire spectrum of photographs and revealing ever more shocking surprises. So, what surprised you from today's video? Was it the possibility of shockwaves in deep space near black holes? Or was it the fact that the Milky Way is home to dozens of little quasars of its own? Let us know your thoughts in the comments below. When the James Webb Space Telescope finally saw the edges of the universe, we knew we had a problem. Webb was able to resolve light emitted from stars 13 billion years ago, helping us to peer back in time to some of the universe's earliest moments. But what we saw was not a sparsely populated proto-universe, where matter was only just starting to coalesce into the first tiny, intermittent galaxies here and there. The early universe was a bustling place. It had galaxies. Too many of them. They were too bright. And the black holes we started to spot in their hearts had grown too big too quickly. Some began to proclaim that our models were wrong and cosmology was in crisis. And while some of these problems have begun to alleviate as better data came in, Other problems simply became more prominent. But in a strange twist, one of the most resilient mysteries in all of this might be about to unravel, thanks to a black hole with an impossibly big appetite. Its name is Lid 568, and we've just seen it breaking the Eddington limit, consuming matter faster than it should be able to, and it might just be the key to everything. I'm Alex McColgan, and you're watching Astrum. Join me today as we explore Lid 568, the Eddington limit, and its groundbreaking implications on cosmology. A black hole breaking physics? By now, I really shouldn't be surprised. It takes time to cook up a galaxy. Interstellar gas and dust need time to subtly come together under gravity until a critical mass is reached and stars begin to ignite. These stars live and die, and from their deaths, new stars are formed. This too takes time. Cosmologists have observed our universe and, based on what they saw, created models for how old our universe is and how quickly galaxies form, which is why the James Webb Space Telescope data caused such a crisis. Things were not as the models predicted. Fortunately, some of those problems proved solvable in the months after the data was released. For example, the brightness of the galaxies we could see through Webb. This brightness implied that there were far too many stars present in those galaxies. So many stars should have taken much longer to form, and yet there they were, fuzzy red dots at the edge of Webb's resolution. However, scientists at the University of Texas studying Webb's Cosmic Evolution Early Release Survey realized there could be another explanation for all that excess light, and counterintuitively, that explanation was black holes. If we work under the assumption that there were massive black holes in these galaxies rapidly consuming cosmic gas, then the intense friction given off by these hungry leviathans as they ate created an excess of light in their accretion disks. This explains why galaxies overall seemed brighter and were throwing off our estimates. Once you add these shining black holes, you don't need so many stars. The mass of each problematic galaxy dropped, and everything fell back into line with the cosmological model. Problem solved. This reinforced how important black holes are to our understanding of the early universe, which was in and of itself a problem, because the black holes themselves broke our models too. In particular, cosmologists struggled with the thorny question of how they'd come to be. For small black holes, known as stellar black holes, there was no issue. Stellar black holes have masses a few to 100 times that of our Sun, and we understand very well how they are formed. They are the collapsed remnants of a sufficiently massive star, and there would have been time for such black holes to form in the early universe. But scientists were struggling with the supermassive black holes, with masses tens of thousands to billions of times that of our Sun, which tend to lurk at the central point of galaxies. And due to something called the Eddington limit, there just shouldn't have been time for these kinds of black holes to have formed where and when Webb saw them. And yet, there they were, and they were numerous. Stellar black holes can grow as time goes on, provided you funnel more mass into them. But how quickly? In 1920, an English astronomer and physicist called Arthur Eddington formulated the idea that there was a limit to how quickly either a star or a black hole could grow. This was because photons carry momentum, a tiny amount, true, but enough to exert a push. This is what pushes solar sails on certain hypothetical spaceship designs, that tiny amount of momentum imparted by photons. For mass to enter into a star, it has to push against a constant stream of photons that are radiating outward, and at a certain level of brightness, not even gravity is strong enough to pull against the flow. This is called the Eddington limit, and stars that brush against its boundaries, such as Wolf-Rayet stars, bright stars at least 20 times more massive than the Sun, emanating powerful stellar winds, are just the slightest nudge away from blowing themselves apart. For black holes, you might think this would be less of a problem. Isn't the whole point of black holes that they don't radiate any light? But their accretion disks are a different story. As we discussed earlier, accretion disks around supermassive black holes can be incredibly bright, particularly around supermassive black holes, sometimes dwarfing the brightness of the stars in the galaxy they reside in. With brightness comes resistance to gravity, and black holes have to obey the Eddington limit too. So even though, given enough time and mass, stellar black holes could theoretically grow into supermassive black holes, it doesn't seem plausible that this actually explains all the supermassive black holes we see in the early universe. Simulations have been run, and although it is technically possible to grow a stellar black hole into a supermassive black hole in that time frame, it would require those black holes to be feeding at near the Eddington limit non-stop since their birth, which just doesn't happen. Black holes in real life often run out of mass nearby and need to wait to run into more, or for more to come to them. To further complicate the matter, we're not completely sure that supermassive black holes are the grown-up version of stellar black holes in the first place. Although it seems like common sense to assume so, scientists have been confused at the lack of the intermediate stage of black holes observable in our universe. To be frank, they've not cited any, at least none for sure. Supermassive black holes are common at the center of galaxies, and there are thought to be 100 million stellar black holes in our Milky Way alone, based on the number we've seen. But intermediate black holes are suspiciously lacking, with only a handful of potential candidates. You would think we'd see a lot more. Struggling for certainty, scientists began to hypothesize that supermassive black holes were instead born in some other way. Many cosmologists have been exploring the idea that because everything was much closer together in the early universe, things might have been dense enough that interstellar dust itself could conceivably have collapsed to form a black hole directly, skipping the star step altogether. If this is true, and there is some evidence to support the theory, then perhaps supermassive black holes were once capable of simply being born that size or near it right from the offset, even if such a thing is no longer possible in our more spread out universe today. But this is by no means certain. But then, Lid 568 came onto the scene, and the pendulum swung the other way again. Lid 568 is a very distant black hole, between 12.1 and 12.3 billion light years away. It's so far away from us that we can't see it at all using visible light. The expansion of the universe has redshifted it all into infrared ranges. But even its infrared emissions were too dim to be picked up by heavy hitters like Hubble alone. It took the Chandra Cosmos Legacy Survey's combined telescopes and the incredible resolution of the James Webb Space Telescope to see it at all. Even then, Lid 568's whole galaxy is a little more than a faint, red and compact dot. But the light emissions from this red dot are revealing. X-rays given off by Lid 568's accretion disk reveal that it was actively consuming matter in its galaxy's heart in a way that no one expected. You see, Lid 568 crucially breaks the Eddington limit, and not just by a little. It's 40 times over the accretion speed limit. It's well on its way to having its license revoked. How is this possible? It turns out that breaking the Eddington limit is, in fact, possible, but only for short bursts or in sneaky ways. For example, jets can help you get around the Eddington limit. If all your photons are being blasted off in a single concentrated direction, all the other directions can eat to their heart's content, with no photon feedback getting in the way of a good meal. There are other possibilities. While Eddington's limit says that once the brightness of the accretion disk becomes too high, all the black hole's food will be blown away, there is a period of time before this happens where a greedy black hole can snatch at the escaping matter and potentially enter super Eddington territory. Like an overeager diner, it might pay for it later, but for a short burst, that level of accretion can occur. If this is true, it might just explain how supermassive black holes in the early universe came to exist. And certainly, LID 568 exists, and is the clearest example to date of a black hole accreting this quickly. That demands our consideration, much like the impossible supermassive black holes themselves. They are there. It's now our job to attempt to understand how that's possible. So, mysteries remain. If LID 568 is accreting matter past the Eddington limit, it proves such a thing is possible. But what of the other strange things Webb saw? Where are the intermediate black holes that stellar black holes ought to grow into, on their way to becoming supermassive? Why are there so many galaxies in the early universe, more than our models should allow? Do direct collapse black holes, ones formed from the cosmic dust itself with no stellar intervening step, really exist? Our models might be on the right track, but something is missing or incomplete. Black holes exert a phenomenal influence on our universe, and there are secrets surrounding them that they guard jealously. But as powerful as the James Webb Space Telescope is, it has not allowed us to crack this mystery. Not yet. But then, perhaps we ought to be pacing ourselves. Thanks to our telescopes, we have seen billions of trillions of stars, and that's a lot of data. Accrete too much information all at once, and it might prove difficult to absorb it all. So says Eddington, and his rule is never to be broken, except, of course, when it is. On the 14th of September 2015, scientists at the Laser Interferometer Gravitational Wave Observatory detected gravitational waves directly for the first time, a stunning achievement that led to the 2017 Nobel Prize in Physics. Why was this significant? Well, here's an analogy. Let's imagine that human beings evolved without the ability to see light. For thousands of years, we'd fumble in the dark, relying on our other senses until, one day, someone invented a machine that could perceive light for us. In time, we'd see everything from the tips of our noses to the farthest flung galaxies. This analogy captures the magnificence of LIGO. It's about much more than proving a scientific prediction. LIGO enables us to perceive the physical universe and understand reality on a new level. Like photons, gravitational waves travel at the speed of light as they ripple across space-time. Their signals are all around us. By listening for gravitational waves with some of the most sensitive instruments ever built, scientists are recording tremors of distant, violent events. The formation of black holes, supernova explosions, and, potentially, exotic phenomena we haven't discovered yet. So, what are gravitational waves? What causes them? And why is LIGO's ability to detect them already transforming our understanding of the universe? I'm Alex McColgan, and you're watching Astrum. Join me today as we learn about gravitational waves, unpack the groundbreaking technology behind LIGO, and anticipate some of the stunning developments that lie around the corner. Gravitational waves are one of the stranger implications of Albert Einstein's general theory of relativity. As we've covered previously, space-time is a model that combines the three dimensions of space and the fourth dimension of time into a single manifold. All objects with mass create curvature in space-time. and objects with a lot of mass create a lot of curvature, which we experience as gravity. A simple way to visualize this is to think of a pool ball resting on an elastic surface and a bowling ball resting on that same surface. The more massive bowling ball will create more curvature. As objects move across space-time, that curvature changes position with them. One of the amazing consequences is that when objects of a certain mass accelerate, they can send ripples across space-time as gravitational energy. While this requires a special set of conditions, namely a very massive object undergoing acceleration, such a cataclysmic event would send ripples or gravitational waves outward at the speed of light. Think of them like ripples on a pond, but instead of water, they travel through the fabric of space-time in all directions. As in the pond analogy, these disturbances become weaker as they radiate outward. To an observer, the distance between objects would appear to expand and shrink as the gravitational wave passes. Mind-boggling to imagine. Yet, although Einstein predicted the existence of gravitational waves, he was pessimistic about our chances of ever detecting them. He thought that these disturbances would be so small as to escape our ability to measure them. And who could blame him? Many of the changes in distance that LIGO seeks to measure are 1/10,000th the length of a proton. Yes, you heard that correctly. 10,000 times smaller than a single proton. And yet, these signals would come encoded with all kinds of information about their origins, when they originated, how far they traveled, and what kind of event produced them. This is where LIGO comes in. It consists of 2 observatories funded by the United States National Science Foundation and operated by MIT and Caltech. Among its driving forces are renowned physicists Kip Thorne, Rainer Weiss, and Barry Barish, all of whom shared the 2017 Nobel Prize for their decisive contributions to the detection of gravitational waves. LIGO is essentially a large-scale and very sensitive interferometer, an invention that's been around since the 1880s. An interferometer essentially measures what happens when light waves are combined from 2 or more sources. For example, you could use an interferometer to test whether light travels at different speeds through different substances, such as through air or water. Even a subtle difference in speed will produce an interference pattern when the light waves combine, much like what happens when 2 ripples on a pond intersect. If the peak of one ripple hits the valley of a second ripple, they will subtract from each other, producing a flat surface. However, if the peaks line up exactly, it means that the waves are in phase and add to each other. This is essentially what the interferometer measures with light. By seeing how in or out of phase 2 light waves are, an observer can infer the relative speed of the waves. And the larger and more powerful the interferometer, the more sensitive it is. Here's how it works. LIGO has 2 observatories located in Hanford, Washington, and Livingston, Louisiana. Why 2? Well, you need at least 2 detection sites to triangulate where the signals are coming from. Each observatory continuously fires a powerful laser at a beam splitter positioned at a 45-degree angle. The laser beam has to operate at around 750 kilowatts, powerful enough to vaporize you completely if you got in its path. The splitter then splits the laser beam perpendicularly. The light in each arm travels down a 4-kilometer vacuum cavity with a mirror at the end of it. The beams then bounce between this mirror and a recycling mirror at the other end nearly 300 times, increasing the distance from 4 to 1,200 kilometers. Remember what we said, with interferometers, bigger is better. After completing nearly 300 trips, the laser beams combine at the beam splitter and head to a photodiode, which is a light-sensitive semiconductor. If undisturbed, the beams will be in phase, meaning their frequencies will subtract each other and no light will arrive at the photodiode. But if there's a gravitational wave, the distance each beam travels will be slightly different, and they'll be out of phase. The photodiode will pick up a signal indicating the presence of a gravitational wave. Now, this is how it works in a perfect world, but in reality, the interferometer is constantly picking up noise. To minimize this, LIGO uses incredibly smooth 40-kilogram mirrors suspended by silica threads. Any particles in the interferometer's arms are also a problem, which is why LIGO pumps the air from its vacuum chambers to 1/1,000,000,000th of atmospheric pressure. But there's another problem. At these minuscule levels, even quantum mechanics are a nuisance because they introduce randomness into photon behavior. LIGO mitigates this with an optical cavity which squeezes the light. This squeezing minimizes the light phase's noise and squeezes it into amplitude noise, which the interferometer doesn't measure. In other words, the quantum randomness will show up more in the height of the waves. Quantum randomness is a fact of life. It can't be eliminated, but it can be shifted. Much as you might move clutter from your bedroom floor to your closet, the chaos isn't gone, just out of sight for the moment. Plus, the goal isn't to eliminate noise completely, but to get the best signal-to-noise ratio possible. That's a pretty good overview of how LIGO works. So, what has it discovered? As I mentioned earlier, LIGO detected its first signal in 2015. Named GW150914, scientists studied the data and learned that it was caused by the merger of two black holes about 1.6 billion light-years away. These black holes, which were 29 and 36 solar masses, became a binary and spiraled around each other until they merged and released a blast in the final 20 milliseconds that was so powerful. Now, get ready for this number because this is what the scientists actually think. It contained 50 times the combined light power of every star in the observable universe. At the risk of sounding crude, that is nuts. I've read this fact many times over, and I still cannot comprehend what it means. Yet, after traveling for 1.6 billion years and finally reaching LIGO, the disturbance was so faint, it moved LIGO's 4-kilometer arm 1,000th of the width of a proton. To visualize this, imagine the distance between us and Proxima Centauri and changing it the width of a human hair. That is the level of precision LIGO was able to detect. If that's not one of the most astonishing feats in human history, I don't know what is. And this was just the first gravitational wave LIGO detected. The second detection occurred 3 months later in December 2015. That signal also came from a black hole merger, which took place 1.4 billion light-years away. Over its initial 3 runs, LIGO recorded more than 80 black hole mergers, and in August 2017, it detected the merger of 2 neutron stars. Named GW170817, this signal was notable for being the first gravitational wave to be corroborated by electromagnetic observations from 70 observatories across the planet. This was a breakthrough not only in gravitational wave detection, but in multi-messenger astronomy. It turns out, LIGO was just warming up during these 3 runs. As of May 2023, LIGO has begun its 4th run with better sensitivity than ever. After its latest round of upgrades, which kept LIGO offline for 3 years, the observatories now have more reflective mirrors, better mirror suspension, and improved light squeezing with lower quantum uncertainty. And this time, LIGO also has the support of Kagura, a new interferometer observatory in Hida, Japan. Kagura is located underground, making it the world's first subterranean gravitational wave observatory and also the first to use cryogenic mirrors. During an engineering run on the 18th of May, LIGO scientists say they already received a signal that was possibly caused by a neutron star being swallowed by a black hole. We'll have to wait a while for confirmation, but If these early results are any indication, LIGO is about to blow the doors off our understanding of gravitational wave generating phenomena. So, what other developments lie ahead? India is preparing a collaborative project called LIGO India, or Indigo, which will help LIGO triangulate better location data. In 2027 to 2028, LIGO will implement its LIGO Voyager upgrade, which will achieve higher sensitivity with 4 times heavier mirrors and higher frequency lasers. And in the more distant future, a 3rd generation facility has been proposed called Cosmic Explorer. This facility would feature 2 new observatories with arms spanning 40 kilometers and 20 kilometers respectively. Remember, with interferometers, bigger is better. But the proposal that really excites me is the Laser Interferometer Space Antenna, or LISA. This would be the first space-based gravitational wave observatory, which would utilize 3 spacecraft in a 2.5 million kilometer long configuration. This interferometer would be so big and so precise, scientists hope it would be adept at uncovering exotic and theoretical sources of gravitational waves, such as cosmic strings and other speculative phenomena. In theory, it could help us stare directly into the fabric of reality. With a planned launch date of 2037, we're still over a decade away, but it's never too early to start counting the years. So, there you have it. An overview of LIGO and how scientists are using gravitational waves to better understand the universe. They give us evidence of extremely remote and ancient phenomena that cannot be measured by other means, and they can be a secondary way to measure observations made by other instruments like the Webb telescope or Hubble. In time, this revolutionary field should allow us to understand the nature of our universe, its history, and even its future. I hope you found this episode as fascinating as I have. You may have noticed this video didn't have any sponsors, and that's because it was brought to you by our astronauts on Patreon. Consider joining our Patreon to keep these videos thriving, even when they're sponsor-free. It's the reason we can research deep into the topics we love, without cutting corners or chasing clicks. Every new astronaut allows us to explore bigger ideas, and make every upload even better than the last. So if you've ever thought about being a bigger part of this channel, join the crew to power Astrum and keep space curiosity alive.